Welcome back to the next video, everybody. Today, we are going to start pivoting our way back toward the conjecture on the analytic continuation of and functional equation of the L function attached to abelian varieties, more or less. And we're going to do that by looking at the analytic continuation of L functions of primitive forms. Okay, so theorem 6, let's let F be a primitive form at level n of weight k. Let's let G be an SKn. And let's just let S be a finite set of numbers such that G is an eigenvector for TP, at least for all primes P that aren't in S. Suppose that the eigenvalues of TP for F and G coincide outside the set S, then it turns out G must be a scalar multiple of F. And so a good catchphrase here is almost all eigenvalues determine primitive forms. Okay, so proof. See CSS chapter 3. I'm sure this is also covered in Diamond and Sherman chapter 5. Okay, so let's pivot back to conjecture 1, which again, more or less says that the L function of an abelian variety analytically continues once you multiply it by suitable things like powers of the gamma function and stuff, and has a functional equation. Okay, so let's apply the theory of primitive forms and new forms and such to the theory of L functions now. Let's let F be an skn chi for some kn and chi. Let's define F wedge of Z to be F of negative Z bar all barred. It's easy to check that F wedge lives in SKN chi bar if F lives in SKN chi. Okay, now the map F to F wedge is unitary with respect to the Peterson inner product, meaning it's inner product preserving, and it preserves the space of old forms, and so it must also preserve the space of new forms. That's standard operator theory, okay? And so we also see quickly that if F is a normalized Hecke eigenform, then so is F wedge. And what that means is this map, F to F wedge, preserves prim K of N. It preserves primitive forms, okay? So now let's circle back to the Wn matrices. Those were the negative 1 over NZ matrices. Direct calculation then shows that if F is an skn chi and is an eigenvector for TP for all primes P not dividing n, then so is F bar K Wn. And if lambda P is the eigenvalue for TP of F, then lambda P prime, I'll call it, which by definition will be chi P bar lambda P, is the eigenvalue of TP for F bar K Wn. So we can relate the eigenvalues of TP, we can relate the eigenvalues of F and of F bar KWN by a simple formula. By proposition 12 from a previous video, lambda prime P is just lambda P bar. And so theorem 6, the one that I just gave you, tells us that F bar KWN is a scalar multiple of F wedge. If we call this scalar kind of naively I to the negative K W of F, although there is a different definition of W of F, we find that F bar KWN is I to the negative K W of F, F wedge. This is just a summary of the discussion we just had above, basically. Okay. Now, if you combine this with proposition 9 from a previous video, you get the following. Proposition 14. Let F be in prim Kn. And let's let lambda of Fs be n to the s over 2 times 2 pi to the negative s times the gamma function evaluated at s times L of Fs, where L of Fs is the L function associated to F. We know that's an L function now. Then lambda of Fs has an analytic continuation to an entire function of order 1, and it has a functional equation given by lambda of Fs is Wf times lambda of F wedge K minus S. Okay. So this is a similar result to the one that we're seeking for L functions of abelian varieties. And we just got it for primitive forms, okay? And this ends our ability to probe the depths of the connection between modular forms and conjecture 1 using purely analytic tools. So further analysis is going to require the study of differentials of modular curves and their relationship to modular forms. And so we'll start looking at that next video. So thanks for watching, and I'll see you then.